This meeting is being recorded.
In this next section, we're going to take a look here at what's referred to as instantaneous rate. So this is the rate instead of over an interval of time, finding an average. This is the rate at just an instant of time. So for example, we can see on this graph over here, if we were to take this point right here, take the tangent and find the slope of that tangent line, that would tell us the instantaneous rate at that single moment in time. So at time equals 0, for example. So we note over here, this bullet point tells us that all reactions slow down over time. And the best indicator of the rate of a reaction is commonly the instantaneous rate near the beginning of the reaction. So for this specific reaction shown here, we see that we have this chlorobutane with liquid water, and we have our product of butanol on the other side with hydrochloric acid. We see that these reactant products are in a 1-to-1 ratio. So our rate of disappearance to, which would be for this chlorobutane, is the same coefficient for the appearance of butanol. So another example, as we move down here, of an instantaneous rate, just to give you something to remind you, is looking at your speedometer. So whatever rate you look at that specific moment as you're driving, that's your instantaneous rate. So let's continue here and let's look at some reaction rates and how the stoichiometry, the coefficients involved with a reaction, would affect the rate comparisons of products to reactants if they're not 1-to-1. So that's what we see here. We see a 2 coefficient in front of this HI gas, and then we have 1s in front of our H2 and I2 gas over here. So what would happen is we would, for the rate of disappearance of our reactant, we would place 1 over the coefficient of our HI and include that negative symbol in this rate equation. And we have the change in concentration over change in time. And then notice that if we're relating it to the appearance of I2 gas, there's no coefficient or no fraction needed because it would be 1/1 because the coefficient is 1. So let's take a look at this generic kind of setup down here. So if we were to generalize this equation here, where the lowercase letters are coefficients, the capital letters represent our species, our reactants and products, we see that we always will place whatever the coefficient is. So theoretically, if it's 1, this would be -1/1A here, would be -1/1. So that would just disappear. And then we would have the change in concentration of A over the change in time. So that's the same setup for the relationship of B's disappearance rate to the appearance rate of C, etc. We could even relate it to the appearance rate of D. So let's translate this idea to the example below. So sample exercise 2, we're given this reaction here. We have 3A plus 2B gives us 4C. So we're asked, or rather we're told here, if the change in A over time equals 5 molar per second, right? The change in, this should really be A's concentration over time. We're asked to find over here the change in C over time. So let's take a look. How could we figure this out? We can say, okay, if my change in A over time equals 5.0 molar per second, and I want to find the change in C over time, I'm going to use that same setup as before. So I'm going to have 1/3 here. I'm going to make that negative, the change in A. So that would be my 5 molar per second. And then I'm going to equate this to the change in C. So that would be 1 over 4, right? And this would be positive over here. And that's what we're solving for. So delta C over delta T. So we can cross multiply and we would end up with 5/3, because this is actually a negative rate, right? This is my rate of disappearance. So we get 5/3 equals 1/2 x, right? And we can solve for our x, our concentration here. And this would give me, sorry, that should be, right, 1 over 4 here times x. Oh, that all disappeared there. Sorry about that. So we have 1 over 4 times x. There we go. Now, when we solve for x, we're going to see that x would be equal to, with cross multiplying, 20 over 3. We can divide that out and get a integer value here of 6.7 molar per second. All right, and let's do one more example of this with the next problem below. So we have here sample exercise 3. So I'll move through this one a little quicker. We have our equation up top here. We're told that the rate of decomposition of this species here is this value here at any particular instant throughout the reaction. So at that same instant, we want to know what is the rate of appearance of NO2. And then in part B, we're going to relate that to the rate of appearance of O2. So let's see what values do we need. So the coefficient here is a 2. So I'm going to have 1/2, and then I'll plug in the rate that's given, 4.2 times 10 to the negative 7 molar per second. And I'm going to set that equal to 1/4. And this is going to be the positive change because this is a rate of appearance of NO2 over time. So what happens here is I have 1/2 over here. If I cross multiply, this will be 4 over 1 times 4 over 1 on both sides. So this ends up just being 2 times this value given here. So we can shortcut that and say that 8.4 times 10 to the negative 7 molar per second would be the rate of appearance of my NO2. And that makes sense, right? 2 moles of that are decomposing to produce 4 moles of that. So that makes sense of this rate here. Now let's look at O2. We have the same coefficient here. So we're going to have 1/2 of that 4.2 times 10 to the negative 7 molar per second. And then we're going to set that equal to, for oxygen here, that just has a 1 for a coefficient. So that would be 1 over 1 times x. So we actually don't have to do much complicated calculation here. This turns into just 1. So we know that x would equal 1/2 of 4.2 or 2.1 times 10 to the negative 7 molar per second.